Good morning, everybody. So I'm going to talk to you today about Unit 4 for Apex. It talks about what a percent composition is, an empirical formula, and a molecular formula, and what the difference is between all three of those. And I'm going to go through the types of math that they go through in Unit 4 Apex with those to help you go through the problems in the quizzes. So let's take a look. What is percent composition? So percent composition basically tells you or shows you the percentage of all the different elements that make up a compound. And sometimes you're going to find them, they'll use the word molecule interchangeably. And really what molecule means is it's got covalent bonding, but sometimes it'll be referred to also for ionic compounds as well. So like, for example, when you're talking about percent composition. So we're going to work with an ionic compound, and we're going to go through the example with, let's say, magnesium chloride, MgCl2. Well, we want to break that thing apart. We want to break it into Mg and Cl, and we want to find out what the percentages for each of those guys are. So how do we do that? So what we do is we basically take the molar mass of this whole entire compound, and we're going to put that into the denominator for both of these. All right. So we're going to go ahead and do that first. So we're going to need a periodic table to do that. Now notice that there's one Mg and there's two Cls. So if we look at the numbers for Mg, Mg is 24.305. And that's grams per mole. That's the molar mass for it. And that one gets multiplied by 1, so we're not really going to do anything with it. For chlorine, however, we're going to double it. So they give you 35.4527 grams per mole. And we're going to go ahead and multiply that one by 2. And then we're going to add those components up together. And so let's go ahead and do that and see what we get. So if we take 24, actually we'll start with the other one. We'll take 35.4527, and we're going to multiply it by 2, and then we're going to go ahead and add it to the molar mass for the magnesium. And that gives us 95.2104 grams per mole is our total. So that's going to end up being our denominator number that we're going to use. So this one's 95.2104. And this one's going to also be 95.2104 grams per mole. Now what's going to go in the numerator? Well, what's going to go in the numerator is just the element itself, so the molar mass for that. So we said that for magnesium, it was 24.3050 grams per mole. And for chlorine, don't forget you have to double because of that too. So when we do that, we're going to get like 70 something. So 35.4527, we're going to go ahead and double that, and that gives us 70.9054 grams per mole. And then we're going to multiply those numbers by 100, because when we multiply them by 100, those fractions will be converted into percentages, and so that will give you the percent composition for this compound. So let's go ahead and do the bottom one. So we've got our 70.9054. We're going to divide that by 95.2104, and that gives us 0.7447. If we multiply that by 100, that would give us 74.47 percentage. Now, what happens to the units? They cancel out for grams per mole. And then we're going to do the same thing for the top one. So we're going to say 24.305. We're going to go, 24.305. We're going to divide that by the 95.2104. And that gives us, if we multiply that by 125.53 percentage. Now, to check yourself, these guys should total up to 100% or pretty close to it. It's going to be a little bit off because there's always a little bit of rounding that goes on when you do these type of problems, but it should be pretty close. So 7 and 3 gives you the 0, carry the 1, gives you the 0, carry the 1, and this one gives you exactly 100.00%. So that's the percent composition for this compound, all right? So I'm not sure if Apex actually goes through this process. Then the second half that I'm going to show you is the type of problems that are in Unit 4, and I think they might have started by showing you what percent composition is, but I'm not sure if they have you do any math, involving this way. I think most of the math they have you do is trying to derive what's called the empirical and the molecular formula for a compound. So let's go ahead and go through an example of that. So this is example 1. And let's go through another example, example 2, where you would go ahead and do that. But before we do that, let's talk about empirical formula. What an empirical formula is, it's like the simplest form for a molecular formula. And a molecular formula is like something like this. This would be a molecular formula, all right? So empirical formula is the simplest whole number ratio of elements in a compound. And again, we're going to use the word molecule and compound interchange, but I like using compound because it doesn't specify covalent or ionic bonding. Sometimes you'll see the word molecule in here when you actually look the definition up. And what is a molecular formula? A molecular formula is this. Molecular formula shows the actual whole number ratio of elements in a compound. So probably one of the easiest examples that I can think of, we'll keep it really simple, would be, this might be, for example, a molecular formula, C3H6O3, right? So that would be a molecular formula. We'll just call that MF. Okay, so what would be the empirical formula for that? In the empirical formula, what you would do is you would go ahead and find basically a number that would be consistent that's in all of these, a least common multiple, and then just divide it out. So what's the least common multiple of these, or not the least common multiple, but what's the number that will go into each of these? Well, it would end up being 3. 3 could go into 3 once, 3 could go into 6 twice, and 3 could go into 3 once. So you're going to end up with the formula, if you divided all of these by 3, if you divided all of them by 3, you would end up with the formula CH2. So that's the empirical formula. It's basically like reducing fractions. If you have, 4 over 4, you can really reduce that to 1 over 1. You can divide 4 into each one of these numbers to get 1 over 1. Or if you had, 6 over 3, each one of these is divisible by 3. You could divide the 3 into the 6, and that would give you 2. And you could divide the 3 into the 3, and that would give you 1. All right, and so that would, and actually that could turn into 2, but that 2 over 1 would be like the subscripts for the empirical formula. So basically take your molecular formula, find a number that will divide into each of these that will reduce them to the smallest form that you can get. Well, 3 goes into all of these, so 3 into 3 is 1, 3 into 6 is 2, and 3 into 3 is 1. Right? So that's how you would do it. So let's work with an example. Let's say that you already know what the percentages are for these compounds. All right, so you've already kind of gone through this math and done that. So you know that the amount of carbon that you have for, and this is just an unknown compound, the amount of carbon that you have is equal to 40%. And you know that the amount of hydrogen is equal to, let's see, 6.71%. And let's say that the amount of oxygen, because oxygen is also going to be in this compound, is going to be the remainder, which would be 53.29%. And all of those would add up to your total of 100 up here. So let's figure out what the empirical formula for this substance would be. So another piece of information that they would give you if they want you to figure out what the molecular formula would be is they would give you the molar mass of this compound. So let's say that the molar mass for this compound is equal to 180.16 grams per mole when you add it all up. All right. So let's go ahead and pretend that each of these percentages are really a mass. So we're going to express those as grams. So we'll say 40 grams, this one's 6.71 grams, and this one's 53.29 grams. And what we're going to do is we're going to look up the molar mass for these compounds. So we take a look on the periodic table for the molar mass for carbon. Carbon is 12.0107. So what we're going to do is we're going to multiply that by the molar mass, which is 1 mole over grams, and that's going to be 12.017. And then we're going to do the same thing for the next one. We're going to take that and we're going to multiply it by whatever the molar mass for hydrogen is. So when we look at the molar mass for hydrogen, it's 1.00794. And that's grams in 1 mole. So all we're really doing here is, if you remember, we're just doing dimensional analysis. We're given this amount, you bring grams down, and then you're trying to convert it into moles. Because that's really what these numbers are down here. They're really like moles of each of the atoms. And so we're trying to figure out what that quantity is going to be. And then we go ahead and set up another one. We're going to go ahead and bring that gram down. We look at the molar mass for oxygen on the periodic table. And we see that it's 15.9994. And then again, that's for 1 mole. And then we go ahead and we just do the math for all of these. And all of the grams are going to end up canceling out. So your unit of measurement that you're going to write down next to these is going to end up being moles. So let's go through those. All right, so we're going to take 40 and we're going to divide it by the 12.0. Oops, didn't come out right. 40 divided by the 12.017, and that gives us 3.33. And I'm just going to take these out to the hundreds place. And then 6.71 divided by 1.0, oops, again, 6.71 divided by 1.00794, and that's going to give us 6.66. And then the last one is 53.29. And we're going to divide that by 15.9994, and that's going to give us 3.33. Right. So now what we want to do is try and figure out, okay, well, let's take a look at all of those, and let's divide them by the smallest one. Well, what's the smallest one that we have? Well, the smallest one we have is 3.33. So we're going to divide all of these by 3.33. And the unit again is going to be mole. And again, what you're going to do, the denominator is the smallest answer. That's what you're going to end up dividing by. It's your smallest answer that you got whenever you did this calculation. The smallest answer we have is 3.33. So we're going to divide them all by 3.33. Well, when we do this one, we get 1. When we do this one, we get 2. And when we do this one, we get 1. So using that information, let's go ahead and separate all of this stuff. Actually, I should include this with this because I was showing you that if you multiply them divide by 3. That's how you get the empirical formula. Okay, this is really the empirical formula. This is the information that gives you the empirical formula. The empirical formula for this example would be that there's one carbon atom, there are 2 hydrogen atoms, and there is 1 oxygen atom. So that is the empirical formula that we have for that. Okay. Now let's figure out what the molecular formula would be, or the molecular formula. So to get the molecular formula, what you're going to need to do is you're going to need to take that molecular weight that they actually give you, and you're going to divide it by the molecular weight of the empirical formula, right? So we're going to take 180.16 grams per mole, and we're going to divide that by, so this is really what the top number is. We're just adding up the numbers on the periodic table for that. And we're going to take these guys and add them up and put them here, and we're going to divide them and get a number. So let's figure out what the empirical formula for that, all of that stuff would be. Okay. So for carbon, let's have it the other way. So for carbon, you've got 12.0, what was it? We wrote it down, 12.017. And we're going to go ahead and add that to 2 hydrogens, which are 1.00797. And then we're going to go ahead and add that to an oxygen, which is 15.9994. And so that gives us, for this number, 30.03 grams per mole. Right. So again, it's the molar mass of your empirical formula divided by the molar mass that they give you. They tell you that the unknown sample here has a molar mass of that. So we're going to figure out what the molecular formula would be. When we divide those two numbers, we take 180.16 and we divide it by 30.03. What's the nearest whole number you get? You get a 6. Okay. So what does that mean? That means that the molecular formula is, remember how I divided by 3 to figure out the empirical formula? We're going to go the other way. We're going to go from the empirical formula to the molecular formula. So we're not going to divide by 3. We're going to multiply by 3 to do this. So we're going to do the same example here. We're going to take these little numbers that are down here, and we're going to multiply them by 6. So that would give us it would be C6. And then 6 times the 2 will give you H12. And then 6 times the 1 would give you O6, right? So that would end up being the molecular formula for this compound. So again, all we did is we basically just took all of these numbers for CH2O and we multiplied them, all of those numbers, by 6 to figure out what the molecular formula would be. So there's an example of how you would use empirical formula to try, or how you'd use percent composition to figure out the empirical formula and then the molecular formula. And these are the type of problems I believe that Apex Unit 4 has you go through. They might give you one of these, but I know that they give you this, okay? So that's it, and the next video that we're going to work with is going to have to deal with more types of mole problems that we were already doing, something called stoichiometry and also limiting reactants. So stay tuned for those in another day or so. Goodbye.